Moments of inertia. Good day, everyone. In this lecture, we will discuss moments of inertia, an important concept in statics and mechanics. We will learn how moments of inertia describe the distribution of area and mass relative to an axis. These properties are widely used in structural design, beam analysis, and rotational dynamics. We will cover area moments of inertia, the parallel axis theorem, radius of gyration, product of inertia, principal moments, Mohr's circle, and mass moments of inertia. Definition of moments of inertia for areas. The moment of inertia of an area measures how the area is distributed relative to an axis. Mathematically, it is obtained by integrating the square of the distance multiplied by a differential area element. The farther an area is from the axis, the greater its contribution to the moment of inertia. The polar moment of inertia is defined about a point or axis perpendicular to the area and is equal to the sum of the moments of inertia about the x and y axes. Notice that the units are length to the fourth power, such as millimeters to the fourth or meters to the fourth. This property is geometric rather than a mass property. Parallel axis theorem for an area. The parallel axis theorem allows us to determine the moment of inertia about an axis that is parallel to a centroidal axis. Instead of performing a new integration, we can use the centroidal moment of inertia and add the product of the area and the square of the distance between the two axes. This theorem greatly simplifies calculations for complex sections and is extensively used in engineering design. Radius of gyration. The radius of gyration provides a convenient way to describe how area is distributed around an axis. It represents the equivalent distance from the axis at which the entire area could be concentrated while producing the same moment of inertia. A larger radius of gyration indicates that more area is located farther from the axis, resulting in a higher resistance to bending or buckling. Analysis procedures. When evaluating moments of inertia through integration, the choice of differential element is important. We generally use rectangular strips aligned with the axis of interest. If the strip is parallel to the axis, direct integration is usually straightforward. If the strip is perpendicular to the axis, it is often more efficient to use the parallel axis theorem before integrating. Selecting the appropriate method can significantly reduce computational effort. Moments of inertia for composite areas. Many engineering sections consist of multiple simple shapes. To determine the overall moment of inertia, we divide the section into basic components, such as rectangles, circles, and triangles. We calculate the moment of inertia of each part, transfer it to the desired axis using the parallel axis theorem, and then add the contributions. If there are holes or cutouts, their moments of inertia are subtracted from the total. Product of inertia. The product of inertia is another geometric property that describes how area is distributed simultaneously with respect to two axes. Depending on the shape and orientation, the product of inertia can be positive, negative, or zero. It becomes zero when the area has symmetry about the x-axis or y-axis. This property is particularly important when determining principal axes and analyzing rotated coordinate systems. Moments of inertia about inclined axes. In many practical applications, the axes of interest are not aligned with the original coordinate system. The transformation equations allow us to determine moments and products of inertia about inclined axes. A special case occurs when the product of inertia becomes zero. These orientations define the principal axes, and the corresponding values are known as principal moments of inertia. The principal moments represent the maximum and minimum moments of inertia for the area. Mohr's circle for moments of inertia. Mohr's circle provides a graphical method for analyzing moments and products of inertia. It helps us determine the principal moments of inertia and the orientation of the principal axes without extensive calculations. The center of the circle is located at the average of the x and y moments of inertia, while the radius depends on both the difference in moments and the product of inertia. Mass moment of inertia. Unlike area moment of inertia, the mass moment of inertia measures resistance to angular acceleration. It depends on both mass and its distribution relative to the axis of rotation. The farther the mass is located from the axis, the larger the mass moment of inertia. Similar to area moments, the parallel axis theorem and radius of gyration concepts can also be applied to mass moments of inertia. This property is fundamental in dynamics and rotational motion. Summary formulas. This slide summarizes the key formulas introduced in this lecture. We reviewed area moments of inertia, composite area calculations, products of inertia, mass moments of inertia, and Mohr circle relationships. These equations form the foundation for analyzing beams, columns, rotating bodies, and structural components. Understanding when and how to apply each formula is more important than memorizing them, so always focus on the physical meaning behind the equations.